One of the biggest selling points of the ESP32 is its integrated Wi-Fi hardware and software stack. Compared to microcontrollers that came before it, it is relatively straightforward to set up a Wi-Fi connection using the provided libraries. I'll show you how to use the Wi-Fi library in ESP-IDF to create a robust connection to your own network. Note that this is a simplified example, as I won't demonstrate things like provisioning and storing credentials for fast reconnects. But know that the concepts and building blocks I demonstrate can be used to create those features. For this demo, you'll just need an ESP32 board. I'll be using the ESP32S3, but other variants should work. Many use modules that have integrated antennas, but if you're using something like this Xiao ESP32S3, you'll need to attach an external antenna. Sorry, but QEMU does not work for this example. The Wi-Fi libraries require physical hardware, so you'll need a real board if you want to follow along. That being said, ESP-IDF supports the OpenCore's Ethernet MAC driver for providing a virtual Ethernet connection in QEMU. This will give you networking capabilities in the emulator, which is incredibly useful for developing and debugging IoT applications. I won't cover this driver here, but I'll use it in later demonstrations, such as for HTTP and MQTT connections. For now, let's focus on writing a simple Wi-Fi driver. Before we start, I want to let you know about my ESP32 IoT course. If you're enjoying this content, I highly recommend checking it out. We start with the basics of ESP-IDF for writing professional code for the ESP32, then learn how to read from connected sensors and transmit that data over Wi-Fi using HTTP REST API calls to an IoT platform. We'll also tackle publish-subscribe mechanisms with MQTT before seeing how to secure everything using Transport Layer Security, or TLS. By the end of the course, you'll have the chance to build a full IoT sensor that publishes data to an MQTT broker, and you'll earn a digital certificate to showcase your new skills. Click on the link in the description to sign up. Espressif has this great document on writing Wi-Fi drivers. It's quite lengthy, but if you read through it, you can get to the part where it talks about what it takes to initialize, configure, and connect. And then you can get an IP address from your Wi-Fi router. In this case, we are going to assume we are using DHCP. This is where the actual initialization starts. You can see here the functions they recommend calling. There is this netif create default Wi-Fi AP, or STA for station mode. While many examples use this does a lot of things in the background, and we're going to break this apart in our code so you can see the building blocks it takes to initialize this driver and connect to a Wi-Fi access point. From there, it goes into the configuration phase. You then start it with this ESP Wi-Fi start, and then you tell it to connect. From there, it assumes by default that it's going to get an IP address from the DHCP client, and we're just going to let that happen rather than forcing a static IP address. There's also ways to deal with disconnected events, which I will show you in a minute, and here's how you de-initialize. It's mostly just disconnecting, stopping, and de-initting. Let's get to writing some code. We're going to create our driver as a custom component. So in the components folder, we're going to say new folder, and we're going to call it Wi-Fi _ STA, not SAT like I have written here, STA for station mode. Then we're going to write Wi-Fi _ STA.c. I'm going to remove this terminal so you can see what I'm working on. We're first going to include some necessary ESP libraries, and that's going to be event, log, Wi-Fi, and Wi-Fi netif, or network interface. Then we're going to include the header file. Before we continue with our source code, we should go and make that header file to establish an interface. Let's create a folder called include. This is where we put our header files. We're going to have a new file here. We're going to say Wi-Fi sta.h. This is our header file. We'll start with our header guards. In fact, I'm going to go ahead and end it here. We will comment the parts of this header file as best as we can. I'm going to use Java doc style, so you're welcome to run something like Doxygen on this to get a nice docs page, but it's going to be fairly simple, so you can just look at the header file. We're going to define some bits for our event group, which I will show you in a minute. You can think of these as single bit flags when an event occurs, and we can use FreeRTOS's event group in order to set and clear flags as well as monitor them in a thread-safe fashion. By default, ESP-IDF has these bits 1, 2, 3, 4, and so on defined for us that indicate the various bits in bytes. In this case, they go up to 32 bits. So this might be 1 left shift 0, 1 left shift 1, 1 left shift 2, and so forth. I don't have these defined right now, but I need to include something that has the base ESP-IDF, and we're going to need ESP-error.h in order to return some of the codes from our functions. Let's save that. And looks like IntelliSense is still not finding that. That's fine. This first function will initialize the Wi-Fi driver in station mode for us. It will then wait for an IP address, and you can wait on the bits in the event group to be set in order to wait for everything to finish initializing. In other words, this function is non-blocking. Also note, as per the documents we just looked at, you need to call ESP-NetIF init and loop create default before calling this function. This is a normal pattern you'll find in ESP-IDF. These two functions initialized everything on the back end, and it should be called by the main app before initializing your drivers. And you should only call them once. The caller will need to pass in an event group in order to set up an event group for this driver so that those bits can be set. We'll also allow passing a null to use the existing event group. This is for doing things like restarting the driver if you've already passed in an event group once, because this function will retain a static pointer to an event group once you've already set it once. Finally, we will return the ESP error type. In this case, it will be ESP OK on success and something else if a failure occurs. Here's our function prototype. We will return the ESP error type. We'll call it Wi-Fi STA init, and we pass in the event group. This is a handle to an event group. Next, we will declare our disable Wi-Fi function, where it returns the same kind of ESP error. We will call it Wi-Fi STA stop, and the caller doesn't pass in anything. Finally, we'll provide a helpful reconnect function that attempts to completely strip down the Wi-Fi driver and then rebuild it back by calling Wi-Fi STA stop followed by Wi-Fi STA init. This will be a very naive approach to this because there are faster ways to try to reconnect, such as by saving your connection details and then reconnecting to the same network. But for now, we're going to keep this driver simple so you can see how to use those building blocks. Let's save this, and we will head back to Wi-Fi station.c. We will set up a tag string so that when we print out debug messages or log them to the console, we'll know where we are in our driver stack. In this case, we know any error messages come from here will be tagged with Wi-Fi STA as opposed to, say, our application. Then we'll set up some static global variables so that this driver has access to them so long as the driver is running. The first is a pointer to the Wi-Fi network interface. We'll then have a handle to the event group that both the application and this can monitor and set and clear bits. Finally, we'll have a handle to the actual driver. We need both that network interface and the driver for this. I personally like to divide up my code into these sections, which makes it a little easier to navigate. The first section will be these private function prototypes. We'll start with the on Wi-Fi event. We will set up an event that occurs so that when something happens, it triggers the event with this callback, and we need to pass it in some sort of argument. In this case, it might be nothing. The event base of basically what was calling this callback, some kind of event ID that we can check to see which event had occurred, and any other information about the event data that's passed in from the thing that's calling the callback. The callback for the Wi-Fi event is for any connection details to, say, the access point at a lower level, and then the IP events are our DHCP, for example, when we receive or lose an IP address from the router. In addition to the two callbacks, we'll also have this internal Wi-Fi start that will allow us to call the various driver elements in order to start up the Wi-Fi connection. Here is where we will define our first event. In this case, it's the on Wi-Fi event that can occur whenever something happens in the low-level driver, such as we get a connection or we lose a connection. I find that the easiest way to handle this is to first figure out what kind of event called this callback and then handle it based on that. So a simple switch case statement works here by comparing the event ID to the available events. We can see which event types are available, but first we need to go to File, Open Workspace from File. I forgot to do this initially, and make sure we open our workspace. Go ahead and save the changes. This should reopen where you were working, but give us access to the ESP-IDF source code. ESP-IDF, here we go. In that source code, we can go to components. We can go to ESP Wi-Fi. In the includes here, you should find one called Wi-Fi types generic. And we can search for that or just scroll down because this has a lot of information about the Wi-Fi driver. I want to say it's around 960 or so. Here we go. Let's close this terminal. You can see the various events that occur. We're only going to look at a few of these, such as start, stop, connected, and disconnected. We can have a default catch-all and just print something to the console if it's one of these events that we're not handling. Let's go back to our main code where we are in our components, Wi-Fi station, open up this, and that's where these definitions are coming from. When we first start the Wi-Fi driver, this event will be called, so the callback will happen. We need to see if we do not have a network interface handle. If we don't, go ahead and call Wi-Fi start. That's one of the ESP-IDF building blocks for creating this Wi-Fi connection, and we pass it in all the relevant information, including our handle to the network interface, the event base, ID, and data that we get that's called when the callback happens. If we get a stop event, then we need to make sure we do have a handle to the network interface. If so, go ahead and call this ESP-NetIF action stop in order to stop the network interface driver. If we get a Wi-Fi connected result, the first thing we do is make sure we have a valid interface handle. If this handle is still set to null, that's an error because we can't continue beyond this. So we just fire off an error message and get out of this function. In this case, it's not the most robust error handling, but it at least lets the user know that something is wrong. Notice that when we get an event start, we then kick off the Wi-Fi driver. That's the underlying ESP-IDF driver. This will start doing stuff in the background. It will eventually fire off this event station connected, assuming it's able to connect to a router. And from there, we take a number of steps in order to get an IP address from that router and establish that full connection so we can start using that Wi-Fi connection to the router and out to the greater internet. In this event where we know that we've connected to an access point, we can then cast that event data as this Wi-Fi event STA or station connected type. We can get the access point information from there, and we're just going to log it out to the console so we can see that we are indeed connected to an access point and get information about that access point. These S2.4 or something markers I'll put in here are the section numbers that correspond to that ESP-IDF documentation page we looked at. These should align with the steps to initialize and connect to an access point using Wi-Fi. So this is section 2.4. Once we know the connection has been established, we want to register this interface receive callback. This is just a callback function that happens on the back end whenever we receive data from that router. In this case, we will get the driver from our network interface. That's more or less just a handle to the backend driver. We will call this ESP Wi-Fi is interface ready when started function. That's another backend building block. And if that succeeds, we will call this ESP Wi-Fi register interface receive callback function to register the callback function. In this case, that callback function is ESP-NetIF receive. That is a function that is already defined for us on the back end, so we don't need to actually write that callback. We just need to make sure that these things are connected. Otherwise, the driver won't work. Then, according to section 4.2, we need to call this ESP-NetIF action connected function. This sets up the full interface and starts the DHC process where we will get an IP address from the router. Assuming we make it this far, that means we have established connection with the router, and we can go ahead and set this Wi-Fi connected bit on our static Wi-Fi event group that the application can then monitor to see if we have connected to the router. Something to note about the ESP-IDF driver, and that is it handles IPv6 requests a little bit differently. We have to specifically request an IPv6 address. So if we enable IPv6, which we are going to set up custom Kconfig symbols to do, then we need to call this ESP-NetIF create IP6 link local and pass it in our Wi-Fi network interface handle. From there, that generates a request to give us an IPv6 address from the router. Without it, we're just going to assume that we want an IPv4 address. Next, we will handle the disconnected event. In here, assuming we have our network interface handle, we're going to go ahead and call this netif action disconnected to tell the backend driver that we want to disconnect, and then we will clear the station connected bit from our static Wi-Fi event group so that the top level app knows that we have been disconnected. As a sort of experiment, if we enable this auto reconnect symbol in Kconfig, we can attempt to automatically call the reconnect function. And that is everything for our connected callback. Next, we will define the event handler for receiving an IP address from our router or access point. Once again, we will write some code dependent on our Kconfig symbols. In this case, if config Wi-Fi station connect IPv4 is set, or connect unspecified, which lets the driver and access point figure out, do we use IPv4 or IPv6, or maybe you get both addresses. If either of those symbols are set, we will go ahead and assume we're getting an IPv4 address here. So we say case IP event station.ip, which is IPv4. And first, make sure that we have a valid interface handle. Let me correct some spelling. Then we need to call this ESP Wi-Fi internal set station IP to notify the backend Wi-Fi driver that we got an IP address. From there, we can extract some information about the IP address of our device, our ESP32 device. The event data that comes in should be able to be cast into this IP event .ip type. From there, we can extract the IP info and then print some stuff to the console. In this case, we can get the IP address from that IP info, the net mask, and the gateway. We will use this IP2string function in order to print all of that information. I'm going to correct my double spaces here. Just like we did for the IPv4 version of getting an IP address, we will have an event handler for when we get an IPv6. Notice that we also set this up with the Kconfig symbols. Those need to be set to IPv6 or unspecified so that we can actually get an IPv6 address, and then we'll handle it here. We will first make sure that we have a valid interface handle. If not, we will just print an error and return. It looks like my indenting is off just a little bit, so I'm going to correct that like so. Like before, we will notify the Wi-Fi driver that we got an IP address, print an error if that function failed. Then we will set the Wi-Fi station connected bit in our event group. If an IPv6 event caused this callback to occur, note that the event data is going to be a little different than an IPv4 event. In this case, we need to cast it to an IP event .ip6 instead of the regular IP event .ip, which we saw in the IPv4 version. This is why we're doing those preprocessor if statements to determine if we're doing IPv4 versus IPv6 or both of them. Here, we'll do the same thing where we get that information, we will cast it as needed, extract the info, and print out the IP address, net mask, and gateway for the Wi-Fi interface on our device. Next, if we lose the IP address, whether the router fails, the DHCP lease is up, or so on, we will clear the bits from the event group to notify the app that we no longer have an IP address and therefore a good connection with the router, and we will print to the console that we've lost the IP address. I realize I made one mistake up here. Instead of Wi-Fi station connected bit, that actually needs to be our IPv6 obtained bit. And let me check on the IPv4 obtained bit. So there we go, IPv4 obtained bit, IPv6 obtained bit, and then we can clear those in this event. Finally, there are some IP events that we didn't capture here. If there's one that we didn't handle here, we're just going to print that event ID to the console. If you're curious, we can go to this enum definition so you can see the various IP events that are supported here. We're only doing a handful of these. Anything else is going to fall through to that default case. Let's close that file. In the on-Wi-Fi event, one of the things that happens is we will do this Wi-Fi start function where we pass in the interface, the event base, the event ID, and the data. If we scroll back up to that on Wi-Fi event, you can see where that function is being called right here. So that just calls another internal function rather than writing everything out here. It just keeps this event handler kind of neat. We will need to store the MAC address of our particular Wi-Fi interface, and we will store the ESP return codes. In case you were wondering why the section numbers were a little out of order in the event handler, that's because this handles a bunch of that section 1 area. In this case, we're going to do section 1.3. This is where we get the net interface driver handle. We can get that by passing in the net interface, and it gets the driver handle out from that. If that driver is null because there was some error in setting it up, we'll just print to console and return from this function. We will need the MAC address, and there is a function in ESP-IDF called ESP-WiFi get IF MAC. We pass in the driver that we just got and a buffer to hold the MAC address. Ideally, this MAC address will be filled with the MAC address of the Wi-Fi interface. If not, we will get an error for our return code, and we can print that to our console and return out of this function early. While it's not needed, we will then print the MAC address to the console so we can see what it is. If you dig into that Wi-Fi default code given by section 1.3 in the documentation, you will find that this ESP Wi-Fi internal register net stack buffer callback is called. This is just registering these internal callbacks to the Wi-Fi driver. In this case, it's the ESP net interface net stack buffer and then the buffer free. That allows the backend driver to allocate and deallocate these buffers as necessary. Next, we will set the MAC address of the Wi-Fi interface. Interestingly enough, it looks like we can programmatically set this, but we are getting the MAC address from earlier from that driver, and we're setting it here to that interface. So we do need to connect some of that driver and interface code, and this is how we're doing it. Once we have all those connections made between that driver and the interface, we can then finally call this pseudo magical ESP-NetIF action start function, where we pass it in a handle to the interface, the event base, the event ID, and any data that had come through from the callback. Remember that this is the Wi-Fi event station start callback, so we assume that the backend driver is just going to pass in whatever event data might be needed here. Finally, in section 3.3, it calls out this ESP Wi-Fi connect function. This is once we have everything else set up, the driver initialized, that interface initialized, we can call this ESP Wi-Fi connect magical function, and it handles the rest of that connection process for us. Note here, we're going to print the SSID to the console, and we're going to get that SSID from Kconfig. This means our application code can be checked into something like GitHub without storing a user's SSID and password. They will need to configure it in menuconfig. It will stay local on their machine and be baked here into the firmware once we build the whole project. So remember, once we start the Wi-Fi process, this event station start will be called. That will call the function we just wrote. That function will then kick off the connection process. Once the connection process happens, hopefully successfully, this event will then occur where we do connect to the access point. We will print out that information and it will start the DHCP process. Once the DHCP process happens, that's another event where we either get an IPv4 or an IPv6 address. At that point, we have set the connected bit and either our IPv4 or our IPv6 bits, which means our app can check those bits to make sure we are fully connected and ready to communicate to the router and outside world. Now, let's wrap all of this up into some public functions that our applications can call. Remember that these are the functions we defined in our header file. So the first is this Wi-Fi station init, and we pass in that event group so we can toggle bits in that group. As per usual, we will need ESP return codes. I like to be explicit, so we will print to the console that we're starting the Wi-Fi in station mode. This is where some of the simplification of this driver happens. If the event group passed in is null, then we won't update the static event group in this particular library. But if we pass in a new event group, then it will update that static variable. If it's still null after that assignment, that's a problem, which means we can't actually initialize Wi-Fi, so we will print an error and return with a fail code. Next, we will create our default network interface. This is going to be using that ESP-NetIF config type. And there is a function ESP-NetIF default Wi-Fi station that just fills out the details of this configuration struct for us. From there, we call this ESP-NetIF new, pass it in that configuration, and we will assign that to our static Wi-Fi net interface handle. If that fails, in other words, it returns null, we'll just print the console and return with a fail code. If we go to the definition of this config, you can see the information that's required here. What is handy is there is this ESP-NetIF default Wi-Fi station that just fills out the default details for us, and we will update it later in our callbacks as we get things like the MAC address and the IP address, and this will get filled out for us. Then we need to create the interface driver. Note that that network interface handle is different from our driver handle. That's why we have two different handles, and a lot of our callback code connects those two together. If we go to the definition of this function, looks like it's not finding it for us. So we will go to components, ESP Wi-Fi. Let's go to that include and ESP Wi-Fi NetIF. So we will copy this, go to this file, and we will search for it. Here's the actual call for this. And there we can go to the definition. You can see it being called here. You can see it actually initializing and allocating memory for that driver and then filling out the basic details. This interface, I suppose an interface type, this is in enumeration, where your main options are station mode or access point mode. Since we are working in station mode, that is why we pass in this Wi-Fi IF STA when we call this function. So this is what allows us to set it in station mode versus access point mode. Here's where the main connection occurs between that network interface and the Wi-Fi driver with this ESP-NetIF attach function. If it fails, once again, we print a console and then return a fail code. Even though we do the main attaching here, those callbacks finalize that attachment once we get things like IP addresses. Now we need to register a bunch of events. We're going to use this ESP event handler register that registers the Wi-Fi station start, stop, connected, and disconnected events along with our IP events. And we're going to pass in the name of the function, in this case on Wi-Fi event, which is the function we wrote earlier to handle these events. So the event base is Wi-Fi event, and that's been defined for us in ESP-IDF, and the actual event is this station start event. The final parameter is any arguments we want to pass in. Since we're not passing in any arguments, we're just going to say null. Note that this registers the event to the default event handler, which the main application needs to start up in order for us to actually do the registration here. Because I am lazy, I'm going to copy and paste this code. And we're going to do that for the stop event, the connected event, and the disconnected event. So there's our start. We're going to change this to event stop. We need this to align. And instead of station start, this is station stop. And we will change that console message. This is station connected. We will change the event to station connected and the error message to station connected. And the last one is disconnected, which we will change the naming here. Instead of start, change it to disconnected. In this case, we were registering the got IPv4 or IPv6 events. The first one is our getting an IPv4 event. We will surround that by our preprocessor, so this only gets compiled if IPv4 is enabled or unspecified is enabled, and we will call the onIP event handler that we wrote earlier. Because I am lazy, I'm just going to copy and paste that. And we are going to do this to register the IPv6 address. So we're going to change that to IPv6 or unspecified. Got IP event becomes got IP6. These are predefined by the ESP-IDF. We will still call on IP event, and we will change that. The last one we need to register is our losing an IP address. So I'm going to take our IPv6 registration and modify that. The event type is now IP event station lost IP. it will still call the same on IP event function. And if something goes wrong, we'll just say we couldn't register the event. Something that section 1.3 advises us to do is to register this shutdown handler. So if the ESP32 is going down, it should gracefully shut down all of the networking interface and drivers. And that's what this register shutdown handler does. It registers on shutdown this ESP Wi-Fi stop function that is internal to the driver. So it's not a function we need to write. Looks like my indentation is off, so I'm going to fix that. And for whatever reason, these aren't a bang. And let's go to the next section. In section 1.4, they have us call this ESP Wi-Fi init, and we will pass in a configuration that we construct the defaults from using this Wi-Fi init config default macro or function. Section 2 of those docs talks about setting the Wi-Fi mode. In this case, we're going to set it to Wi-Fi mode station as opposed to access point. This is where Kconfig is going to help us allow the user or developer to choose the minimum authentication mode for Wi-Fi. There are a variety of Wi-Fi authentication modes available, and we're going to let them choose it in menuconfig. In this case, we will allow open, WEP, WPA, WPA2, some combination of WPA and WPA2. All of those have pre-shared keys along with the WPA3, and then that combo of WPA2 and WPA3, as well as WAPI. Whatever the developer picks for the application, this will set the minimum authentication mode that is allowed by this driver. If you're using WPA3, note that it has a couple of different ways to set passwords or enable encryption between the devices or stations and access points. The two main ones are hunt and peck mode and hash to element mode, or you could set a combination of both. We won't get into the details of WPA3 here, but note that the driver does support them and the user or developer will have to choose them in menuconfig. Next, we configure that Wi-Fi connection by filling out this Wi-Fi config struct. In the station field, we will fill out the SSID, which we get from Kconfig. Same with the password. We will also set that authentication mode that is determined by Kconfig, hence all those #ifs and #elifs that we did earlier, as well as the WPA3 SAE modes. If you set a hash to element identifier for WPA3, we pull that from menuconfig as well. Finally, we call this ESP Wi-Fi set config function in order to set this configuration that we just created and print a console and fail if something goes wrong. Finally, we call this ESP Wi-Fi start to kick off this whole process. Once it enables everything, it will call that on Wi-Fi event callback with the Wi-Fi event station start event. That will then kick off the rest of the setting up of the interface, connecting it to the router or access point, and then finally obtaining an IP address for us. If something happens, we will want to be able to stop that driver, so we're going to write that here. We will need that ESP return code for some of these functions. The first thing we will do is unregister all of those events. As I mentioned earlier, that this driver will tear down everything rather than trying to gracefully stop and restart. It's a brute force method of stopping the driver, tear down everything, and then reconstruct the driver if you want to start it again. It's not the most efficient, but it is simple and hopefully much easier to understand what's going on. I'm going to copy and paste these unregistration events. It just makes it a little easier. We will repeat this to unregister the stop event, and then we will unregister the connected event, and then we will unregister the disconnected event, which should be all of our events for that Wi-Fi event group. We need to do the same for the IP events, which includes first unregistering the got IPv4 address event. I'm going to copy and paste and do the same for the IPv6 event, which is just changing a couple of the characters here from 4 to 6, basically. Finally, of these, we will unregister the lost IP address event as well. So I'll just copy and paste that in and change the event type to lost IP address. Make sure that gets unregistered. If not, print an error message and fail out of the function. Then we will unregister that shutdown handler that we established earlier. We will unregister the ESP Wi-Fi stop function. If that has already been unregistered, that's okay. We'll catch that return value, just print info to the console. But otherwise, if there's a true failure, we will return with a fail code. Next, we'll call this handy ESP Wi-Fi disconnect function to disconnect from Wi-Fi. If that returns codes that state either the Wi-Fi is not initialized or it's not started, we can assume that the Wi-Fi has already disconnected, so we'll print that to the screen. Otherwise, if there's a real error, we will log that as an error and return a fail code. I'm going to go ahead and put these in extra parentheses. And in fact, I'm going to bring this down here so it's a little easier to read, like so. After we disconnect from Wi-Fi, we can then stop the Wi-Fi driver. Once again, if it's already been deinitialized, we will just print that to the console. Otherwise, print a real error message. Even though we stopped the driver, we haven't fully deinitialized it, so we need to free up those resources by calling this ESP-WiFi deinit function. If it's already been deinitialized, we'll just print it to the console. Otherwise, log a real error message and return a fail code. Finally, we will destroy the interface driver and set the handle to null. And then we will destroy the actual interface itself. If we manually call this Wi-Fi stop function, it means that we are no longer connected, so we should go ahead and clear those event group bits anyway. This will let the app know that a disconnection event has occurred and we no longer have an IP address. Here we will set the network interface handle to null. In fact, this is only one handle. We will print a message to the console showing that the Wi-Fi has indeed stopped and all of the functions before it successfully completed. We will return the OK code. Finally, we will create this simple reconnect function that just calls the stop function and then calls the init function back to back. We'll need to store those return codes. The first thing we'll do is just call that station stop function. If that doesn't work, we'll just throw an error. And then we will restart the Wi-Fi connection. Notice that with the init function here, we are passing in null for that event group because we're just going to assume that the developer of the application has already passed in an event group when they call that init function once, and that has been saved in a static handle. So we pass in null, so we continue to use that same static handle, which means they don't have to keep passing in the event group into this function. Once again, if initialization fails, we'll log an error. And we are done with the source code for our driver. Let's save that. And now we need to make a custom component in ESP-IDF by adding a few extra files. With the source for our driver written, we have our header file, our source code. Let's make a CMakeLists.txt. We will set our sources and include directories. These are variables we will append to these lists as needed, and then pass those to the IDF register components function. We're going to have a Kconfig symbol called Wi-Fi STA connect. If that's enabled, go ahead and add the Wi-Fi station.c source code to this list. Then we will register the component using this IDF component register function. We will pass in the sources, which is given by this srcs variable we declared at the top of the CMakeLists file, as well as the include dirs. So this will include all the source and header files that we created as part of this component. We also need to include some libraries or other components that are part of ESP-IDF. Hence, this private requires ESP-WiFi is a component and ESP-NetIF or network interface. Those are two different components that this component relies on as dependencies. Because they're private, they're not really passed up to anything, including this component. So the application won't have access to anything that is in ESP-WiFi or NetIF unless we include them specifically. Let's save that, and I'm going to make one little syntax correction there. Save that again. And now let's make our Kconfig file. Notice that the spelling here, just like CMakeLists.txt, is important, as ESP-IDF will look for that when we are going into things like menuconfig. We will declare a top-level menu item called Wi-Fi station configuration. Under that, we will create a symbol called Wi-Fi Station Connect. That's just a regular Boolean on or off to enable or disable this particular driver. We will give it the description of connect using Wi-Fi, default it to no for disabled, and create a better description here, a longer description that says enables the Wi-Fi driver to connect to your local network. If the Wi-Fi Station Connect symbol is enabled, it will open up these other options for us. This is what allows us to do those submenus within menuconfig. So under that, we have this choice of Wi-Fi station IP type. This is where the user can choose the IP version. So they have the option of IPv4, IPv6, or unspecified, where the driver and router get to choose which one to connect over, depending on what's available on either of those. Unspecified says that the driver on our ESP32 should be available to work with IPv4 or IPv6, and then whatever the router or access point uses, go with that. The first option is Wi-Fi Station Connect IPv4 that says use only IPv4. Similarly, we have the same for IPv6, where we specify the symbol, give it a Boolean to enable or disable. Notice that the select here selects something else in menuconfig. In this case, it's going to select the LWIP option for IPv6. We did the same for IPv4. This enables the LWIP drivers for IPv6 or IPv4 that's lower level in ESP-IDF. So this is how we turn stuff on or off using menuconfig. So when a user or developer selects this particular option, those other options are automatically selected for us. And I have one slight misspelling here. I want to make sure this says IPv6. There we go. Finally, we will define the unspecified choice that allows either IPv4 or IPv6. And to do that, we have to enable both drivers for LWIP, IPv4, and IPv6. Here's where we allow the different choices for the Wi-Fi authentication mode. It will default to WPA2 pre-shared key, but we will allow the user to select among open, WEP, WPA, WPA2, that mix of WPA, WPA2, WPA3 only, WPA2 mixed with WPA3, depending on which one you go with or which one the access point supports, and WAPI. We will have a string. This is Wi-Fi STA SSID, where the user can enter the SSID or the network name for the access point to connect to. Then along with the SSID, we need that password for all of the PSK or pre-shared key options. Remember that these get passed into our driver when our code gets built. Then we'll define the SAE mode if you're using WPA3. This is another choice that allows you to choose between hunt and peck, H2E or hash to element, or both of them. Here we'll enumerate those three options. So we have hunt and peck, we've got hash to element, and we have both. Note that we are going to default to both. If you are working with WPA3, you will want to dig into your router to figure out which of these options you should use. If you're using H2E mode, you'll need to set a password ID. So we're going to have a string here that allows the developer to set that. It will default to nothing, but note that it does depend on H2E or both options being set in the choice above. Finally, we have that auto reconnect option. Should you as a developer want to try it, when that disconnect event occurs, if it happens because you lose power to your router, for example, this will attempt to auto reconnect. In reality, you're probably better off trying to reconnect from within the app when you identify such an event. That allows you to save any states or anything you're working with and allows you to reconnect more gracefully rather than relying on the driver to do it on the back end. But it's here in case you want to try it. Let's save this, and we are ready to create a very simple demo application using our driver code. Let's create our Wi-Fi demo. So in our apps section or our apps folder, we will create Wi-Fi demo directory. In there, we will create main and main.c. We'll start by including some libraries. In this case, we will need the string standard library. We will need ESP event, ESP log, the network interface, FreeRTOS for doing things like sleeping the main thread, and our non-volatile flash. We will also include the Wi-Fi station header file that we just created from our own custom component. We will define a connection timeout of 10 seconds. So if we don't establish a connection, then the function will fail and we can just print that to the console, and we will sleep our main thread for 1 second. Just like we did in our Wi-Fi station driver code, we will create a custom tag string. These debug messages will either be Wi-Fi_STA for our driver code or Wi-Fi demo for our application code. That allows you to differentiate where these messages are coming from. Then we will define app main as our entry point. We will need a few variables, in this case, the return codes. We will need a handle to an event group and some event bits. Once per application, we need to call this NVS flash init. This is our non-volatile storage area that the ESP32 Wi-Fi driver uses on the back end to do things like store Wi-Fi settings. We won't be calling this explicitly, but know that it is available if you want to do things like store the settings between reboots. Also, if there are no free pages, meaning it's out of free space, or if there's a new version of the non-volatile storage, driver in this case, go ahead and erase everything that's in the flash and then reinitialize. If there are any errors with this, print it to the console and we will just abort. Note that we are using the ESP error check macro here when we call the NVS flash erase function. That does the same thing as checking ESP return code against ESP OK. If it's not equal to ESP OK, go ahead and throw a message and abort. Next, we will call ESP-NetIF init to initialize the TCP/IP network interface. Once again, we only need to call this once in our application, and we must do this prior to initializing the network driver. That's the Wi-Fi station driver we just wrote. And then we need to create the default event loop. This is a loop that runs in a thread in the background that allows us to do things like register events, unregister events, and then handle those events with callbacks, just like we set up in our driver code. Note that I'm calling these three functions, initializing the flash, initializing the network interface, and creating that default loop in the application code because you might have other drivers that rely on these rather than putting these three functions inside of the driver code. These should only be called once. The other thing you could do is, say, set a global flag somewhere once they've been called so that you don't try to reinitialize them. I find that you can call them more than once, but they tend to throw errors when you do. As a result, I just put them once at the beginning of the application code. Finally, we get to call our Wi-Fi station init function that we wrote in our driver code. We will pass in the handle to that event group so that it can set and clear bits in that event group. If there's any failures, we'll just print an error to the console and abort the whole program. Note that Wi-Fi station init is non-blocking, which means our application code can go on to do other things. But in this case, we just want to wait for the connection to happen and for us to get an IP address from DHCP. First, we will wait for that connection to happen to our access point. In this case, we're going to call the FreeRTOS function xEventGroupWaitBits. We pass in the handle of our network event group, and then we tell it which bits we want to wait for. In this case, we're going to wait for that connected bit, which should be bit 0. PD false is a FreeRTOS thing that is essentially false versus true. This third parameter is clear on exit, which says to clear the bits once this function returns. We don't want to clear those bits. We want to leave the connected bit as it is once we return from this function so we can continue to check it in the future. So we will set this to PD false. The fourth parameter says to wait for all bits. We only have one bit, so we're just going to say true, wait for all of those bits, in this case the singular bit, to be set before we return from this function, and then we will set a timeout here. In this case, it's 10 seconds. And because it's FreeRTOS, we need to use this PD milliseconds to ticks macro and pass in our timeout constant, which is 10,000 milliseconds. Note that this function returns with the bits that have been set. We can mask it with the bits we intend to be set, in this case, the Wi-Fi station connected bit. If so, we print that we have connected to the network, or we log an error and exit out of the program. We're going to do the same thing while waiting for an IP address. In this case, we're going to use xEventGroupWaitBits. We'll pass it in the same event group, but we will use the IPv4 obtained bit and IPv6 obtained bit. We will OR those together and wait for one or both of those bits to be set before returning from this function. Or the timeout occurs of 10 seconds. If we get an IPv4 address, we'll print that we've obtained such, or if we get an IPv6 address, we will print that as well. Otherwise, print that we failed to obtain an IP address, usually if the connection timeout has occurred. In this case, we don't actually want to wait for all of the bits. So we want to wait for either IPv4 or IPv6 bits to be set. So we will change this fourth parameter to PD false. Finally, we have our super loop. Even though this is in a thread, we will make sure that we are still connected by masking the network event bits with the station connected bit to make sure that the station connected bit is still enabled. If so, we will print that we are connected to the Wi-Fi network. If we've lost the connection, we'll print that and exit out of the program. We will also delay 1 second between each iteration of this loop, just to give us something to do while we watch this print out to the console. Let's save that. I'm going to close my driver code up here. Let's create our CMakeLists.txt inside of our main folder. We will define our IDF component. We will include the main.c and no extra include directories for our application. Then we will make our CMakeLists.txt file at the project level. We will define the minimum required version, which is 3.16, and include that ESP-IDF CMake extension that's at the ESP-IDF path, tools, CMake, project.cmake. We'll use this list append function to add the components. This is our custom components to that extra component DIRS variable. And then we will give our project a name, which we will call app. With all of that done, let's bring up a terminal. We'll start in workspace. We will navigate into apps Wi-Fi demo. and we will set the target. In this case, I'm going to be building for the ESP32 S3. Give that a moment to run. Once that's done, call idf.py menuconfig to bring up menuconfig. If you go down to component config, go all the way to the bottom, and you should see our Wi-Fi station configuration that we added as part of our custom component. Press enter to go into that. Press space to enable connect using Wi-Fi. This is where you can adjust using IPv4, IPv6. You can adjust your minimum security here. I'll leave it at WPA2 since that's what my network uses. You can give yourself an SSID. So this would be the access point SSID. I'm going to make something up here. And then you would change your password here to something, whatever your network password is. This is for WPA3 only if you're using that. Same thing for this password identifier. And then you can attempt to automatically reconnect, but I'm going to leave that disabled for now since we don't really need it. Press Q to get out of this. Yes to save. idf.py build to build our project, and hopefully this builds. It looks like I have a couple of errors. I probably forgot semicolons. So let's scroll up to see what's going on here. I have lots of errors. Let's fix a couple of these. So we will go here. It looks like I have log. This should probably be log E for error. And I will continue to fix these. So I just recompile and see what happens. Wi-Fi.stop. It looks like right here. I forgot a semicolon. Sure enough. Good old C. Try again. Implicit declaration makes me think I either misspelled that. That looks okay. Or I probably forgot some include here. Let's try this. That gives me access to some of those internal functions. Try to rebuild. Still a few more errors. That's not right. It looks like I have a bad semicolon here. Let's try to build that again. And I misspelled these. That should be capitalized. That should be capitalized. And then same here. All right. Try building that. Network group is uninitialized. So in main, before we initialize our non-volatile storage, it looks like I forgot to initialize the event group. So we will call X event group create. Check to see if it's null. If not, that's an error. So we'll just throw that and abort the program. Let's save that. Try building again. It looks like we're good to go this time, which means we can go ahead and flash it to our actual ESP32 board. Go ahead and bring up a terminal on your host computer and navigate into this repository directory. Activate the Python virtual environment and go into the Wi-Fi demo that's in Workspace Apps. Then we will call python-m ESP tool. This will flash the binaries for us, give it the port for your chip, in this case, auto-detect the chip, give it a baud rate, tell it to reset before and after flashing, tell it to write flash, use dual I/O mode, and a flash frequency of 40 megahertz. We'll let it auto-detect the flash size, and we will set the addresses for the bootloader.bin, the partition table, and the app binary. That should flash for us. So give it just a moment. And then we will call miniterm that's part of PySerial, give it the port and the baud rate. With any luck, you should see it restart. And hopefully you see it connect to your access point. You see it connect to the SSID. It should say connected to Wi-Fi network. This is coming from the demo versus the Wi-Fi station. After a moment, it should say Wi-Fi IPv4 or IPv6 if you selected that address obtained, and it should print out the IP address of the device. This is the IP address of my ESP32 on my network. It should also give you the net mask and the address of the gateway. The demo or main application should say that it has obtained an IP address, whether that's v4 or v6, depending on the settings you configured in menuconfig. And then it will just sit here and print out still connected to Wi-Fi network over and over and over again, unless you say pull the plug from your router. That means your Wi-Fi driver is indeed working, and you are good to go to start creating other applications based on this, such as HTTP requests, using TLS, or even MQTT. Networking is foundational to creating IoT devices, and it can often be tricky in microcontrollers. Luckily, ESP-IDF makes it easy to build robust drivers to handle communication protocols like Wi-Fi.